Wow, welcome to your first video of the year, and not really because I meant to, but I feel compelled to explain a few things prior to your test. So your first half of the test will be on Friday of this week, and I know it's not the best to do it on a Monday, but that's just going to have to be how we roll. Thank you, Snow. All right, so I wanted to show you this limit at infinity that we didn't get to in class, as well as another example, and then I'm going to show you three popular questions that people had been asking on the homework. All right, so when I look at this problem, I've got the limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1. So because of this square root, when I'm trying to figure out what the heck the end behavior is, my normal rules for finding horizontal asymptotes don't apply because of that symbol. So I can revert back to the fact that I can divide the numerator and the denominator by the highest power of x that I see. So the highest power of x I see in the numerator is x to the first. And technically the highest power I see in the denominator is going to be a square root of some type of x squared. So it's also x to the first. But I'm going to be strategic. When I multiply by the number 1, which is what I'm allowed to do, I'm allowed to multiply any expression by 1 and it stays itself. I am going to, remember, dividing by x is the same as multiplying by 1 over x. So I'm going to multiply the numerator by 1 over x. Well, I'm also going to multiply the denominator by 1 over x so that I keep this as 1. However, I'm going to be strategic in how I represent it. Instead of writing it 1 over x, because this would ultimately give me the square root of 2x squared plus 1 over x. And since this is a value or an expression that is contained outside of a square root, and this one is contained underneath the square root, algebraically, there's really squat I can do with it. So what I can do, however, is I can represent x as the square root of x squared. Now, I want to make note that we're talking about as x approaches positive infinity, so we are assuming that x is greater than 0 as we are doing this. And this fact will become a little bit of a sticky wicket when I do an example problem from your homework. All right, so as we move on, I have the limit as x approaches infinity of 3x over x minus 2 over x when I take this value and distribute it to those terms. And then when I multiply this across, I'm left with the square root of 2x squared plus 1 over the square root of x squared. All right, in my next step, the limit as x approaches infinity, I get 3 minus 2 over x, and I can rewrite this with just a single radical. All right, so the limit, now I'm going to start evaluating the limit. I don't need my limit notation anymore. Okay, the limit as x approaches infinity of 3 is just 3. The limit as x approaches infinity of 2 over x is of the form 1 over x to the r, so that's 0. Down here, here's what's going on. If I simplify, I have 2 plus 1 over x squared. Well, think about this for just a minute. I know I cannot algebraically do this. This is incorrect. I can't think of it like that because that would be like saying 16 plus 9 is the same thing as the square root of 4 plus the square, or I'm sorry, the square root of, I was right, square root of 4 plus the square root of 3. And that's not true. It's equal to the square root of 25, which is 5. But if we use our brain, as x gets increasingly bigger and bigger and bigger, a big number, 1 over a really big number, isn't this itself, this number, it is approaching 0? So if I'm taking the square root of 2 plus some number that's almost 0, it's just the square root of 2. The limit of this amount is just the square root of 2. So the limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1 is equal to 3 over radical 2. This is going to tie into problem number 27 from the homework set, so let me explain that next. All right, so we just finished this example. Now let me show you how this relates to problem 27 in your homework sets. So this one is just a little slightly different. In problem 27, they want you to take x approaching negative infinity instead of positive infinity. So this is how it's going to affect the problem from the previous example. In this case, we want to know what are our x's doing on the left side of this graph, or as x gets really, 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 really negative. So if that's happening, your x's need to be less than 0. I don't need that written over there anymore. All right, this is what we have to assume. So in doing so, when I look at this function, I can't determine a horizontal asymptote by our regular horizontal asymptote rules. So I'm going to divide the numerator and the denominator by the highest power of x we see. And keeping in mind that even though I can't separate those terms, a square root of an x squared, it would be an x to the first would be my highest power that is really represented in the numerator and the denominator. So I am going to write dividing by x is the same as multiplying by 1 over x. So I'm going to do that here. But instead of writing this as 1 over x, I'm going to write 1 over the square root of x squared. However, because I want my x's to be negative, I need the outputs to be a negative x. So because I'm taking the limit as x approaches negative infinity, I need to make a negative on the outside of that x squared, square root of x squared. So moving forward, it's very similar to the last problem we did. As the limit as x approaches negative infinity, x times 1 over x gives me 1. When I take the square root of x squared minus x squared times 1 over negative x squared, remember this is a negative on the outside, and I can write it as x squared minus x all over x squared. So I have the limit as x approaches negative infinity of 1 over negative square root of 1 minus 1 over x. Again, the limit, if I evaluate the limit as x approaches negative infinity of 1 is just 1. And in the denominator, as x is getting really small, okay, so it's negative a million, negative a trillion. The negative and the negative would cancel to be a positive. So right here, this is really adding or subtracting nothing. 1 over x is headed towards 0. That's what it's approaching. So if you're taking the square root of 1 minus something that is really small, ultimately it's just the square root of 1. This negative comes to the outside. So that's how I get negative 1 for problem 27. All right, here is another example that I didn't have time to show you in class, and then I'm going to do problems 31 and 33 that go with it. So here we want to find the limit as x approaches infinity of the sine x over x. I'm going to explain it first using the squeeze theorem so that you can concretely see why this works. And then I'm also going to explain it where some of you might be able to just look at this and tell me what the answer is. Okay, so the limit as x approaches infinity of the sine x over x. Well, my normal asymptote rules aren't going to apply. So factoring doesn't really work here. There's nothing I can factor. There's no algebra I can do. There's no radicals. So what I do know is when I see things like sine x or I see things like cosine x, I know that they have a range restriction. So let's try squeeze theorem. I know that the output of any sine of x is going to always be between negative 1 and 1. Okay. But I don't want to know what the sine of x is. I want to know what the sine of x over x is. So I'm going to go ahead and divide this entire compound inequality by x. So now if I take the limit as x approaches infinity of negative 1 over x, the limit as x approaches infinity of the sine x over x has to be squeezed in between their two limits. Well, negative 1 over x and 1 over x is of the form 1 over x to the r. So they are 0. So that means the limit as x approaches infinity of the sine x of x by the squeeze theorem also has to be 0. Here's another way that you can also think about it. If you were like, okay, now I don't know that I really like any of that. Well, if I cover all that up and you want to think about it, this is an informal way to think about squeeze theorem. You know that the numerator right here, as x approaches infinity, if I'm taking the sine of 5,000 degrees, the sine of 1 million degrees, I know that this output is always going to be between negative 1 and 1. Meanwhile, my x is getting really big. So you are getting a really big denominator with a numerator that's always going to be between negative 1 and 1. So no matter what value I have on top, if I'm dividing by a really big number, then that number is approaching 0. So that's kind of another way that you could think of this. All right, so let me show you how this problem relates to problems number 31 and 33. It's not exact. These are still some thinking problems, but just trying to show that correlation to the homework sets. All right, on problem 31, All right, so this is what I had some students say to me. They said, Nap, can I use squeeze theorem on this? And my answer is yes. I can actually maybe show you, let me show you two algebraic ways to go about this problem. If I do the squeeze theorem on this, all right, the sine of 2x. Well, if x is pi over 2, then wouldn't this just be pi? If x is pi over 6, then this would be pi over 3. In other words, the sine of 2x would still have a domain, or excuse me, would still have a range between -1 and 1. If I divide everything by x, all right, then when I take their individual limits, all of them as x approaches infinity, then the same thing holds true. This limit right here is going to be squeezed or sandwiched in between 0, so that's why the answer to that is 0. Here's another approach. I know that the sine of 2x is a double angle formula, so I can think of it as 2 sine x cosine x. Now, if I want to break this up, these are not sums. This is a product. So I can think of this as 2 over x times the sine of x times the cosine of x. And because this is of the form 1 over x to the r, I know that this limit is 0, so it doesn't even make a difference what the limits are here, because 0 times this limit is still 0. So that's another way of thinking about it. Another way of thinking about it is if you don't even show any algebra, it's the same idea. If I think about the squeeze theorem informally, as x is getting really, really big, my denominator is getting really big, so I have a really big number. And in my numerator, I'm taking the sine of some type of angle, but that output is always going to be between -1 and 1. So if you're, again, taking some type of number between -1 and 1 over some really, really big number, it is approaching 0. All right, and let's do 33, and that will be the end of this video. Hopefully you'll find this helpful since I was unable to be here, and then we had snow, one of those things. All right, the limit as x approaches infinity of 1 over 2x plus sine x. So again, let me show you how squeeze theorem can work, and then I'll show you how you can also kind of reason your way through it. All right, I know that the sine of x has a range between -1 and 1. Now, I don't know what sine x is. I want to know what sine x plus 2x is, so I'm going to add 2x to this compound inequality. All right, now, I need to reciprocate all of them. So if I'm going to reciprocate, that means I'm going to change the signs. And 1 over the sine of x plus 2x is going to be sandwiched in between 1 over 1 plus 2x and 1 over -1 plus 2x. So again, let's think about this, friends. If I'm going to take each of their limits as x approaches to infinity, so I'm going to do that with all three. If I am taking 2 plus some really, really, really big number, and then I just subtract 1. Well, this is 1 over some really big number, because if it's a really big number, subtracting 1 is still going to make it really big. So this limit as x approaches infinity is approaching 0. It is the exact same conversation for 1 over 1 plus 2x. If I am taking a really, really big number times 2, and then I add 1 to it, it's 1 over some really big number, so it is approaching 0. Therefore, the limit is sandwiched or squeezed in between those two, so it's also 0. Another way that some kids were thinking about it is if I take 1 over 2x. The 1 over the 2x part, 2x as x gets really, really big, is a really big number. The sine of x is always going to be something between 1 and -1. So if you're taking a really big number, and notice how I am informally doing the squeeze theorem, because I'm talking about this one and that -1, adding a really big number to those isn't really going to be that big a deal. So that's another reason why this limit is 0. All right, so for your test, you can do any of the problems on the Chapter 1 review, which is on page 91 and 92. And then your limits at infinity are from Chapter 3, problems 33 to 44 on page 243. On Friday, you will have a no calculator part of the test. It is worth, I think it's like that part of the test might be like 57 and the other one's 43 on Monday. So Friday, there's no calculator part of the test. And on Monday, you will have the calculator portion of the test. And for those of you in 6th hour that I haven't been able to meet for the last 2 days, I will say that I feel pretty comfortable giving you the test. The first quiz you guys did a dynamite job on. My goal is to hopefully get the WPEs graded and try to come to school Thursday morning so the sub can hand those back to you, and so that you have some feedback. So study your WPEs, study your homework, and study the chapter review, and I think you'll be very prepared. Good luck. Feel free to email me with any questions.